start recording. We're going to the presentation. Once again, this is all online, and you can see it on my log. So with that, I'm going to share my screen for everybody. Entire screen. Allow sharing the screen. So let's go to full page slideshow. All right. So, okay, what is a 3D printer? So this is an example of an open source 3D printer by the company called Lulzbot. But all you're talking about for the 3D printing is a gantry, a moving head that spits out some kind of a material, whether it's metal, plastic, steel, or anything else, or glass, or anything. And there's different ways. It either spits stuff out, or it moves in a complex 3D shape in order to do some activity upon material in a three-dimensional way. So for example, you can have a plain 3D print like what you might be used to is things which spit out molten plastic, or things that spit out molten metal. That would be a welder head upon a 3D gantry, and that's called wire arc additive manufacturing. So that's 3D printing in full metal for big shapes like tractor frames, for example. Plastic is common. I also mentioned the possibility if you embed actual fiber inside the print, then you have fiber reinforced plastics. It's a high performance plastic route. You can have things like a laser head on top of a 3D printed 3D gantry hitting some kind of a material, whether it's metal powder, whether it's sand or fine sand, so you can be actually fusing the material that's underneath, such as metal, to get full high quality metal prints, or things printed in actual glass as the laser heats the substrate, melts it, fuses it together layer by layer. It's like in a sand bed or in a metal powder bed. You can do things like that. Now this is very common. The parts, if you do open source, then the parts on this kind of a machine are only about $300. It's quite affordable. This happened in about 2012. The open source RepRap project took over the world. It's the patent on what's called fused deposition modeling ran out, and the RepRap project started at a time, and it brought the cost down from tens of thousands of dollars overnight to hundreds of dollars, and the whole 3D printing world exploded, especially in the DIY world, and in fact, then like a lot or most of the current 3D printing industry that you see out there is based on open source projects when the patents ran out about 2012. 3D printing can be used with things like cement. So you're printing in cement. The head carries cement and big mixing. I mean, this is no joke. This is really, behind this is heavy machinery that moves and prepares the cement. So this is heavy industrial stuff. If you talk about printing in concrete, the structures that are big as homes, and then many people brag about Chinese homes. Oh yeah, 3D printed a house in a day. Blah blah blah. Yeah, cool, but I mean it's kind of cheating because walls are once again only 20% of a house in terms of cost and effort. So yeah, you can print some things, but it's much harder to 3D print all of it, such as the utilities and everything else. But it's doable too. Like if you can do, say, wood, plastic composites, you can 3D print channels like your electrical boxes, even your plumbing, everything right at the module level. That's the direction we're going. Get the bigger 3D printers up and do work where the entire module can be, for example, printed in 3D, including like any kinds of mounts, trim, conduits, boxes, plumbing, other complex geometry, including insulation, multi-wall material that traps air that now turns the 3D print into insulation. It's exciting. You can print straight with mud. This is like if you were to go to Mars, you're gonna have a lot of rock around, and put a little binder in it, and you can build structures right out of the material under your feet. And this is exciting because I mean, compressed earth blocks. It's similar. This is like Adobe automated plus complex geometries. I think it's cool. It's you're using a natural material. You can also add binder to it, and then you have much stronger structures that are rainproof and so forth. If you print with plain mud, it'll melt in a rainfall event. But yeah, you can do all kinds of small 3D printed objects like the cordless drill. I mean, that's kind of fake. That's only just like the shape of a cordless drill. It doesn't look like it has the interior parts. But any complex device like your drills and saws and everything, it's basically a bunch of plastic, some heavy-duty machined metal parts, a battery, and some electronics. So 3D printing does get you a lot in terms of the actual production of any kinds of these tools, or what I mentioned about the open source everything store like the Amazon that you can do if you have open design and access to all the high-tech components that exist out there. You can build the structure, you can get high-tech components, and you can be doing effective custom production of just about anything on a garage scale, pending the availability of open design, which is currently largely the missing point, because you can't really get good design for just about anything, and a lot of things that are really good, they kind of hide and become proprietary, and people are selling them and not sharing the actual blueprints.
Do you have any idea what the break-even point would be on something simple, like let's say like a junction box? Like how expensive would the printer be? How much are you paying in plastic?
Yeah.
How much would it cost to run versus $2 at the store for a junction box?
Yeah. So you're talking about print costs, and I'll go over the figures there, but the bottom line print cost is a kilowatt hour per kilogram. So a junction you can print for, if you have solar energy off the grid, it's costing you about 10 cents to print a kilogram. So that's like, what, 50 boxes? Now, what about the operating cost of the actual printer? The filament costs, now it costs a lot. It costs 20 bucks a kilogram. If you're gonna build, say, how much does each box weigh? Like maybe 1/20th, maybe like 20 per pound or something. Say you print 20 of them, you're paying $1 in just the plastic that's off the shelf commercial plastic. That story completely changes when you start making your own 3D printing filament with your open source extruder, at which point you're talking about $50 per ton of waste plastic, say in a plastic bale, right? So at that point it becomes extremely attractive, pending your availability of open source machines to shred and make that filament. So it becomes absolutely realistic, but it's not practical. Say you want to print 2x4s that weigh 10 pounds, well, that's going to cost you $100 in off-the-shelf printing filament. But if it's, say, 10 cents a pound from a garbage bale, right, then what does the cost become? You're paying now, for 10 pounds, you're paying effectively $1 in materials for a 2x4's worth. And then on top of that you have electricity, but that's like 10 cents per kilogram off the shelf. If you go solar, also a game changer. The open source PV system, say for the CDECO homes, what we build right now is getting us 1 cent per kilowatt hour. Game changer again. So effectively you reduce the energy cost to zero. So say, okay, 1 cent per kilowatt hour because of the 30-year lifetime of PV and the amount of, you can go through these calculations. I'm not BSing you, just go through the numbers, ask ChatGPT, how much energy does it take to print a kilogram, how much does off-grid solar actually cost if you buy those solar panels right now at 20 cents a kilowatt hour? A kilowatt, sorry, not kilowatt hour, per kilowatt capacity. So a 500 watt panel, like half a kilowatt, is now costing you $100, which is insane. I mean, that's like, people don't recognize how insane that is. It's like literally like talk about free electricity, free energy kind of stuff. I mean, all the freaks talk about free energy. Well, free energy is there in an industrial system in the form of photovoltaics already. Now, when you get the whole systems installed, it's kind of different because your contractors and everybody else are going to charge you quite a bit to do the install. If you know how to install it yourself, the cost goes way down. It goes way down when you integrate the PV into the house build up front, so you don't have expensive retrofit costs. And that's where it makes sense. I'll talk a little bit more about the cost structure. But 3D printing in metal, that's actually an open source 3D printer by one of our friends. So that's wire arc additive manufacturing. You've got simply a welder head, and you've got a moving, it's actually an inverted 3D printer moving that structure around, so you can 3D print objects in solid metal. this is the 2012 history. RepRap open source printer project. That's perhaps the most important open source project to date in terms of actual impact, because right now hundreds of millions of dollars are being made by various companies that do sell 3D printers. Once again, they are based on this project, and you see this kind of looks like our stuff, which is like simple rods and everything exposed and all that. And yeah, that's you can build it like that. And now, yeah, the original RepRaps. That's a copy. That's the idea. There is that parent printed all the 3D printed parts, so you still take the rods, you buy them off the shelf, but all the components around that, all the 3D prints, make for another 3D printer. So you have the idea of self-replication. Yeah, and you can continue that on and on, so that for about a few $100, or very very lowest cost, like $100, you can literally do that. And we've done a frame that's made of rebar that works. You do 3D printed corners and rebar. It's a cool idea. So what's related to 3D printing in our set? So you got the bioplastic extruder. So a machine like that gets you that filament at near zero marginal cost. You've got the 3D printer itself. You've got a shredder. So say you're shredding bales of plastic to make filament. You're melting that down. You can be adding cement or sawdust into the actual cement you can 3D print with cementitious materials. You can use 30% sawdust in your regular plastic prints from your sawmill to make 3D printed plastic lumber like material, which is made of sawdust and plastic together, composites, things like that. So yeah, it's about building more machines and then building materials with some of the Global Village construction set technologies. So including things like glazing, lumber, plastic lumber / sawdust composites, insulation, as I talked about, the idea of multi-wall glazing with cavities which traps air, that therefore is insulating, because a 3D printer is a perfect device to print complex geometry. Or you can 3D print basically failed prints, which are known as spaghetti. Basically, it's like bulk fiberglass. It's just 3D print a print head that moves fast and just throws that plastic in very fine strands all over the place to make like a spongy mass. That could be somewhat insulating, and that probably could be developed to an insulation material. But once again, that's not in the current system where that plastic filament is costing you a lot. But those opportunities are huge when you take charge of actually doing your own recycling and filament making to make this absolutely economically feasible.
Do you have a way to make filament?
We've done it before, so I'll talk about that. So more machines are cool. We use a thing, I'll tell you about that. So we use, when we talk about anything, we talk about construction sets, including the 3D printer. So we have a thing called the universal axis. It's just your one-dimensional part of a 3D gantry system that makes for the three-dimensional motion and therefore production. The universal axis is just a simple thing which is scalable though. So on a wiki page called Universal Axis, you'll see how we build these things with simple like 8mm rods. Universal CNC axis, this is just the basic unit. You put X, Y, and Z and you've got 3 dimensions. It's as simple as this. Those are the printed parts, the complex off-the-shelf part, which is a stepper motor, a couple of bolts. And that's all that goes in. There's a belt and rods, and you make various things, like this bigger 3D printer that we built, or this taller 3D printer that we built, and things like that. So take a look at this, and we can scale those axes up. Now in this case, you've got 1-inch rods, and that's for a pretty heavy-duty machine. You can very easily make, say, a 4x4 machine that's got 1-inch rods, super stiff, super precise, and that's the smaller 3D printer axis for size comparison right on it. And we've even gone up to larger than that. So this is, you can study the whole system of how we do this with the parts. Various people have replicated. We've done all kinds of different frames. We also went up to, so yeah, you just 3D print the parts and so forth. We also went up to, in this thing we have up to 2-inch universal axis. So this is now getting into heavy machining territory. So you got to use bigger components, but we built a machine that like heavy metal frame with these big bushings for 2-inch axes that are this huge, like this. So you can scale this. Once again, the beauty of scalability, modularity, construction set approach is that you can build these. Now this is industrial grade. That's a thing you need to lift with a chain and stuff like that with the large axle. We didn't finish this, but this is readily upgradable, readily doable for heavy duty machining. So that's the universal axis. We also used magnetic mounts. I like magnets. They're pretty cool, like with the magnetic location of the boxes. Here we actually built 3D printers where the frame's attached, so you can modularly like modify this to various configurations. You're just attaching with the heavy duty neodymium magnets to metal, or making larger machines and so forth. So you can do all kinds of different things, including like multiple print heads, in which case your print rate, maximum print rate of any print head that's out there is about 20 pounds per day. So if you have like a 9-headed 3D printer, that starts adding up into kinds of amounts where in 1 week we can actually produce all the plastic lumber. Say we use that in a house to start replacing the actual lumber that we use in a significant way. And if you're going to do that commercially, you of course have to get that certified and licensed by regulatory bodies. And you have to get that engineer to say that, oh yes, this actually works as these properties, and then you can go forward. But if we publish all that openly, then you're talking about open source engineering, you're talking about distributed quality control ability, because you have the documents that support what you're actually doing. So for housing, these are so this is what the idea there is: off-the-shelf printer plastic, very expensive, like $20, maybe even $10 at the cheapest per kilogram. That's completely not doable. Like, you can't print any structures with it. Go ahead.
Have you ever made 3D printable plastic out of stuff, or seen people make their own?
Oh, you talking if
like
we made our own filament?
Trash making.
We did. I'll show you right here. So you can take regrind or pellets at regrind from the trash stream, about $1 a pound. Garbage bales at about 10 cents a pound. If you do your own recycled plastic, it's free.
And you can just make them to high quality.
You'd have to have quality control. You have to control the quality of your feedstock. If your feedstock is clean, then you're going to get good plastic. If not, then not. Here's an example of an open source filament extruder. We built a similar one compared to that. Where is that thing? We built one here it is. Here's ours. We built this. So it's a little extruder. In 2 hours, we got a spool of filament. So we used regrind, or like little pellets, and we made our own. And then you can also just take trash plastic, you can shred it, make it into little balls or whatever.
How do you make sure they'll work well as filament?
It depends on what you have for your feedstock. If you know you have ABS that you got from a bumper of a broken car, it's okay, it's pure ABS. If it's clean, it's going to be clean ABS. So it depends completely on what you have, and there's a whole game you have to play to understand the properties and all of that.
So this is how you did the biochar thing for the fish stock?
No, this was just making a roll of plastic.
But you want to do the biochar thing.
We want to do the biochar in a sense that you're embedding biochar in your 3D printing filament as a growth medium. So that's another crazy application. We're looking at that right now with our collaborator in Mexico for actual replacement of cocoa coir in agriculture operations, which is a big deal because cocoa coir costs a lot. But here, OSC electricity costs 1 cent per kilogram. The amount of energy you need per kilogram is about a kilowatt hour. So if you buy that electricity off the shelf, you're talking about 10 cents in energy costs. If you've got an open source energy system of photovoltaics that you installed, you're going way down into like a single cent territory per kilogram of plastic, which makes it completely affordable on a production front, even for large scale things like plastic lumber. And if you're going to do that, that takes another that doubles your energy cost. But now you're at 2 cents per kilogram if you're making your own plastic like this. So you have to count, yeah, it's 1 cent, but then it doubles because you're going to make your filament first and then 3D print with it. But there's also other ways where you can take the pellets directly and 3D print with those already, though that may not be as controllable or accurate. It's not as robust, so I'd rather make the filament in tight controlled environment. Therefore, I can do very high quality prints, very small size, also larger size prints from the same kind of system. From shredder to extruder, Precious Plastics is an open source project out there that has the full chain of shredders, extruders, and other plastic forming machines, but they don't have 3D printers, which I think is a big miss on their part. But you do have access to a lot of open source machines that can get you into that filament, your own filament production. Definitely a high priority because we're talking about 20,000 or so lumber, 20 to 30,000 per house lumber cost. About half of all the materials is structural lumber stuff and OSB. And that's the kind of stuff you can be 3D printing. And I just think it's a very low-hanging fruit situation there. The printers exist, the shredders exist, it's system integration, and really it's about heavy machines lifting big bales and shredding on an industrial scale to make things like building your own home from the waste stream and plastics that you recycle a reality. But it's completely doable. I mean, it's not cheap. It involves all kinds of equipment. Off the shelf, of course, this kind of equipment is prone to fail and expensive. So in an open source route, if you can add lifetime design to that kind of a system, you've got a robust way to take housing to zero marginal cost. Because then you've got digital fabrication, your 3D printers are printing your modules, it's just much easier. So we definitely see a lot of this possibility coming up in the future for real production. And we have done, like, just to give you a simple example, what kind of stuff we've done. Okay, that's FreeCAD. Draw yourself some double wall glazing, put it on a print bed. Takes 3 hours to print this thing, 73 grams, 1/20th of a pound, and that's what you get. That's just polylactic acid. It's a bioplastic, 3D printed, it's semi-transparent. But you can also print in, I mentioned about polycarbonate, the high-performance industrial plastic that a lot of the high-performance greenhouses are made of that. The multi-wall glazing is made of polycarbonate. It happens to be a thermoplastic. You can melt it, and you can print it again. The disadvantage is that you can only recycle about 5 times, because every time you recycle, the chains of the actual plastic molecules shorten up, and it becomes more gummy than strong. So you kind of lose like 20% every cycle. That's still like you retaining 80% of the original through every print cycle is awesome. And then say you're printing a house materials, I mean, you're not going to take that down for 100 years in principle, so you don't need to recycle that multiple times.
Could there be any harm to living in a plastic house, like breathing microplastics or something?
Yeah, I mean, I'm sure there could be. It depends what kind of, if you got food grade plastic versus toxic plastics or whatever. There's going to be all kinds of plastics, so you want to go for ones that are safe. Like polyethylene is pretty safe if you don't have a lot of toxic additives to it. Polyethylene, polypropylene is your cutting boards. That's what cutting boards are made of, so that's food safe. There's many kinds of food safe plastic and body implantable plastics as well. It depends what people add to them, like plasticizers or UV stabilizers, whatever other chemicals for various properties, such as flame resistance, like computers and electrical cases may be made of plastic where they add additives that the thing just doesn't burn, but it's also toxic if it does burn, if you light it on fire. So the chemicals they add to it are pretty nasty. So yeah, potential is huge there. I think with doing things like the hempcrete, where we are even printing hempcrete block. So we're talking about mixing some form of biomass with cement that we make through the solar concrete route, using photovoltaics as the energy source to burn limestone and turn it into concrete. Yeah, those are things that are possible pretty much off very common materials, because limestone is right under our feet here, and that's what makes concrete. And then plastic is quite abundant, so you can do a lot of it, and then you can source the metals. I mean, there's plenty of junkyards around that already highly refined metals that that are just waiting to be used. So there's a lot of potential if you use solar energy and open source machines to do that. I think I'll quit at that. And yeah, we've sold 3D printers before. We built a printer that was up to like this huge thing where the bed got so heavy that it was hard, it was too hard to lift it. But yeah, rubber too, thermoplastic urethane, things like rubber wheels or rubber tracks, like puncture-proof tires. How about that? You can print for about $80 in 3D printed plastic. You're talking about, say, a skid steer wheel that's made of thermoplastic urethane, which is a thermoplastic. Lifetime design things that, because a wheel like that off the shelf costs you like $1,000 a pop, for a puncture-proof tire that doesn't have air. You can print complex geometries for the tires. You can do things like rubber belts for drives and things like that. O-rings for pressure cylinders and pressure systems and things like that. There's a lot of thermoplastics available to do that. So it's exciting. It's a technology that can definitely be used for some good. Any other questions? Any questions on the topic of 3D printing and construction? Sam?
Do you foresee being able to print more complicated materials in the next 5 years or something?
I think so.
Like a big scale 3D printer.
Yeah, I mean they already exist for whole homes, right? Like huge gantries, as I showed way up front there. You take a house scale gantry, and that's what does this. Like this is a full size house. Those walls have been done by a large gantry.
What are they made of?
So they're spitting out concrete mixes.
Oh wow.
Yeah, and it's so your system can make lattice walls like that, so it's more efficient than using concrete. How it uses it, but there's no limit to how big that machine can be that you put. It's like basically moving cranes in 3D.
That are just programmed.
Yeah. So say you have say we wanted to build the hangar with a 3D printer. You would put a big set of tracks around it, and you'd have this 3D print head, say it's spitting out concrete like this in a lattice form, or even your bioplastic with wood mixed in it. So you can do that. There's no limit, no theoretical limit to how big those gantries can be. It's like maybe in space you've got space frames, like satellite scale things. Space frames, gantries, like cranes. Cranes are space frames. These lattice structures, they're huge, and they can build or erect very large structures. Like skyscrapers are built with cranes like that, right? So effectively put some kind of a 3D print head on a crane that's precision motion controlled, and there you go. I think a lot about, so there's a lot of these windmills around here. I think about taking some kind of a gantry system which just pretty much like prints that big tower, layer by layer, and then you got that, because those things are expensive and shipped from far away, and these big trucks. You can do that from say local resources and with wire arc additive manufacturing. It's not a high-tech technology. It's just you have to have the equipment available to do this kind of stuff.
Yeah, that's SpaceX. They use 3D printers to print their rocket engines now.
Yeah. I mean, crazy stuff is happening.
Yeah.
And those would typically be, you've got your vacuum shredded metals, so very, very fine metal powders that are printed, so the print chamber is filled with inert gas or partial vacuum, and you shoot that powder with a laser and it fuses. So layer by layer, so you can create a very complex shape like a jet engine. The thing there is, it's a more high-tech thing that includes lasers and a clean environment with inert gas, such as whatever argon or helium, whatever they use there. Because if you use a laser upon any kind of metal, it would oxidize, it would turn to rust. So you have to have it in an inert environment to do that kind of thing. But yeah, I mean, you can do crazy things right now. That kind of technology, you can pull a vacuum or get industrial gases to do that kind of stuff. That's no big deal. The powders that are made, they're made by, how do they make them? I think that it's like at very low temperatures they do ball mills to basically pulverize metals into very, very fine powders to make those kinds of metals in an inert environment. You have to evacuate the air from that, because that would turn into rust or oxidation if you don't have that kind of environment. But yeah, that's basically what it is. It's fine metal powders that are laser sintered. Yeah, go ahead.
So this looks like they have a big factory with that they'll 3D print all these houses in and then just roll them out. Have you ever seen people use like little like RC car type things that 3D print and just keep going layer up, print another layer, and then just jump up another layer on the house?
Yeah, I mean that's another way to do it. Yep. I can't point to specific projects that I know that are actually commercially viable doing that. I don't know if anybody else knows any, but
so, do you think there's a place to include like injection molding in a similar vein of this?
I don't like injection molding because every single injection mold is custom fabricated, where you can get the same kind of geometry through 3D print means
But
without.
you could fabricate the molds with the 3D
You
printer.
can, but then you're probably talking, if you're talking about molds, you're talking about huge volume production, and then you're getting back more into this mass economy as opposed to like meeting local needs. So there's some affordances of a system like that. If you invest so much money into producing like 1 million of something, then there's a lot of industrial inertia that tends to build up, and you get back into the kind of system that we have today where there's huge inertia in an industrial system that keeps things a certain way. So just by like basic principles, I'm not a huge fan of it. Yes, you can do those molds, and if you can have a simple way that you can then melt down these molds and reuse them.
Talking about making pellets, and I mean, when I was in school, like, we had a small handheld injection molder. So like you put the plastic pellets in, and it was a lever, to inject it. And so something like that could be feasible for something like outlet boxes that you're going to make dozens of for each project.
Yeah, it could be, but you have to see that. Yeah, that's more capital intensive on actual infrastructure that does do that, because that 3D printer can do the exact same thing, and we'll have. I mean, maybe like it'll take longer, but still, energetically wise, energy is not really an issue with the solar power being so inexpensive these days. So you can just go slow and let it go overnight, as opposed to either a fully automated injection molding system or a person manning that and pulling a lever all day. So I'd rather do the automated route where I don't have to worry about it, and then you can get into the world of digital fabrication where you've got your, like right now we could be talking about this, but I could hit send, and in a hangar we've got a 3D print going on right now. I think that's really cool because it gets you into that full digital economy of abundance of potential zero marginal cost. So that's cool.
And also, when you're 3D printing these houses, I don't see too much of that going on in this picture. But how easy would it be to either, while they're 3D printing the structure, lay down pipes and stuff, so like it finishes a layer and then it says pipes need to be laid here, here, and here.
Yeah.
Do it, and then it'll just print over the pipes, or print holes in the 3D printed structure. I don't know how well that works with concrete.
Oh, absolutely, it works really well. Well, for concrete, it may have some collapsing issues.
But you would still need a electrician or someone who is going to do an electrician's job to go and wire it and put the pipes in. But you would have the structure pre-built for quick pipe and electricity.
Absolutely. Yeah, you're designing like basically all the dimensions and all the geometrical properties into it. And I mean, there's 3D printed circuits these days. You can be laying down metal that in channels.
Yeah, and then you could potentially, what I'm thinking is for a house that size, have one man do all of the interior stuff in one day. That is the potential for 3D printing, because everything's laid out.
Everything is laid out, absolutely. Like
you just
today, the kind of stuff we were doing, if every single box was marked, because it was already 3D printed, like you put a little sign, okay, box goes here, you can even 3D print that in your model.
Hole in the wall just to slap it into.
All the holes, penetrations, geometries that you're doing by hand, that can already be done. And yes, that's where you exactly have that. Like in a day, you just come in and fill in the missing parts that a 3D printer would have a hard time with.
Yeah.
So you can collaborate with machines that way. So it's always about collaboration. It's not like either or. You want to be using these tools and collaborating with them. Cool. Yep.
And it also says Chinese company 3D printed 3 houses in a single day. It sounds like, because it's not saying that Chinese company is printing 10 houses every day. It sounds like they aren't actually at a production where they can make 10 a day. It sounds like they just are like, oh yeah, we finished 10 in this day. And
it may be just that they're printing the shell, so it could be
Yeah.
that could be marketing gimmickry here, where they call it a house, but it's just walls.
Yeah.
Walls are not a house, you know. But a lot of people do say that kind of stuff. Yeah.
I had a question about powering the machines
Yeah.
that would eventually build out things like this. From the standpoint of solar, is it efficient enough in places farther away from the equator, like, let's say Alaska, or places where there times when there isn't enough sunlight, compared to, like, you know, winter versus like summer?
I would say the answer depends on the cost of PV. If the cost, okay, so take 10 years ago, Germany says, oh, it's almost cost effective to make Germany all solar, right? Jump 10 years forward, and the price of PV jumps 10 times lower. It actually makes it feasible for a place that did not be able to do it before to do it now. So it depends on that. And then of course you can store, so when we talk about hydrogen, storage is a big deal, so generate solar hydrogen. When the sun is out, do that. You can put in more capacity to do those functions. So say in Alaska, if you have half the sun, you have twice the photovoltaics, let's say. And it may be doable. So I don't know. And I don't know how feasible it would be to just ship. Okay, so now in the solar hydrogen economy, you have a global network of pipelines where you can produce stuff at the equator, ship it farther north. But that sounds kind of like more like the centralized economy. So you want to do it on a smaller scale. And you certainly can. I mean, you can start creating your private hydrogen pipelines all over the place to connect the 1,000 global villages worldwide.
That would be very expensive. My dad talks about like how much it is to create gas pipes to go just from Anchorage, like just going like 100 miles.
Yeah, but I must say also, this is in a current economy with very expensive labor, machines that are designed to fail and all that. Like you're counting in all the inefficiencies of the system. If you wanted to, it boils down to how much energy does it take to make a pound of steel and then roll it into a pipe. That number is a kilowatt hour per kilogram of steel melted in an induction furnace. It's about the same for that as plastic. So I'm paying a cent to generate that. If I have open source metal rolling machines, as in a set, I can do that near zero marginal cost. So it depends how you do it. It's certainly very expensive today, and you've got global supply chains and all that, and people competing under the super scarce economy where all the fossil fuels have been the equivalent of 11 days or 10 days of solar energy that hits the sun, hits the earth. That figure, remember I mentioned? How many days does it take to create all that fossil fuel that the earth enjoys? It's 10 days equivalent of energy hitting the surface of the earth. Google that, study that. I'm not BSing. We're living like this kind of statement comes from an economic system where yes, it's expensive and it's scarce because we're living on fossil fuels. They're scarce. They're super scarce. They're a little blip in the history of humanity and not sustainable. So in a future economy, those kinds of systems, like where you have a global interconnected grid of lifetime design power grid that's made by open source machines and much lower cost, it's a feasible proposition. I'm not opposed to it. Like I used to be much more into like, oh yeah, it gets into all this centralization until I found about the power of technology by doing all this stuff, right? So I started welding and 3D printing and doing other things, building things, and I found, well, whoa, this actually works. There's like this amazing technology that we have access to. Like the first brick press that we built, I was hoping for 3 bricks per minute. We got 10. This stuff works, so it's the power is out there, and it's at that point it's the question of do you have access to energy, and the answer is yes. There is very low cost PV energy right now, and it's made from sand, refined silicon dioxide, refined into silicon to produce low cost energy. That's a possibility.
Panes of glass.
Yeah, you can do that through laser sintering, for example. And they also have some actual print heads that are melting, induction melting glass powder to do exactly that. There's things out there like that. I don't know how feasible it. I haven't really studied the economics of that because I would just take. I guess I would take glass and melt it in induction by induction heating or take sand and melt it to make pane glass. And go like more the regular process of how people make glass, because you're talking about some seriously high temperatures for that at that point. So on 3D printing, you would have probably a lot of heat loss in a system like that. But then again, wire arc additive manufacturing, where it's a super high, it's a plasma, it's a melted piece of wire in a welder kind of a configuration. That's super hot. That's thousands of degrees. It's a plasma, and that works. So maybe glass could be, someone could make a feasible way to do practical 3D printing in glass too. But they do that. You can definitely laser sinter as a way to do that. And then it may not be as clear, but some refinements could probably make it pretty clear.
So when I go home, like, what can I just like get from the wiki and just make immediately?
You can build for example, the filament maker or the 3D printer. You can replicate the 3D printer as is right now immediately at a cost of about maybe $300, $500 depending how you source it. I would do that. I mean, that's I just went to get those magnets. Those magnets are back from our 3D printing days, which we kind of quit in 2019 after COVID and moved it much more into housing. But that's exciting stuff. You got some Arduino controllers and stepper motors and 3D printed parts, and there you go with 3D printers that can do magical things. I would definitely get into it, because then you're integrating your FreeCAD skills, your design skills into real things that you can print. And think about a 3D printed house. Think about building 3D printing just regular Lego blocks. I'll leave you with this. Imagine, we've got now OSC is expanding, the movement's growing, and we've got 10,000 people with 3D printers. In 1 hour, we get all those printers running. In 1 hour, we have like a bunch of Lego blocks like for a real house build, and you just put them together. I mean, think about that. A swarm-built house where like 1,000 or 10,000 people 3D print each a tiny part. All you need to do is print like a kilogram, and then build a house with it. We actually thought about doing an extreme build workshop like that, where we crowdsource, we design like a full house, complete full house that can be 3D printed, and you just have each person print like a pound of it. So with 10,000 people, you're printing like 10,000 pounds, which is a house, So that would be interesting. I think that's an interesting exercise to do in practice too. I mean, it's a huge coordination exercise. It starts with design, so the integrated design that allows you to break apart a whole model into something that's 3D printable in small parts. And you can also think about, okay, we're going to actually 3D print the plumbing in there. We might 3D print some rubber inserts that provide like watertight fittings, and even like metal wire. Like you can do in a set we have the wire and rod mill, but think about this, like basically take a wire making machine, you melt plastic, you feed it into a filament extruder that puts plastic around it, and that's wire. It's like plastic coated wire right there. You could be 3D printing with just a continuous strand of something like that. Of course, with the challenge being how do you cut it, but you can find ways to cut it. But if you think about printing, like, so you got very, very fine spring steel wire, which is 140,000 psi strong, super strong. That's embedded in plastic, and just melting that through a regular nozzle. That would work like today, right now. I don't think anybody's done that. I haven't seen that, but imagine metal embedded 3D plastic prints that can be pretty strong, because you've got that embedded metal right in it. So you're talking about plastic metal composites out of a printer. That's not much different than what we're building right now. So there is a lot of possibility. And what I'm saying is like easy concepts. I mean, you got to execute on that and actually develop a full viable, tested commercial machine. But that's that where it comes to that hard work and the endurance to actually go through that development process, which few people have the energy for.
When the Tesla robot comes out, would you get one to set this up?
Is it open source?
No.
If it's not open source, I wouldn't really care much about it, because it's still the same trap.
There is an open source robot under development.
There's many open source robots under development. that's the industrial robot is part of the set. Think about now your skid steers have a heavy-duty industrial robot arm in front of them, so they can help you move things much more effectively than forks or grapples. Yeah, that's all doable. Yeah, go ahead.
So I'm looking at the bottom right video.
Yeah.
Is that for strength or insulation? Because
it's more minimization of material for the same strength. They're using lattices.
It could also be for strength if you use it in engineering and structural engineering.
It is strength with the minimal amount of material.
Imagine
so that's an advantage right there.
Hitting the outside wall, how far it would need to travel to make it there. It would need to travel through the side pieces, and then there's a middle plate that would need to travel all the way from the middle plate to another of this.
Yeah.
And then out to get to the interior wall. It seems like it would also help with insulation a lot than just doing a straight thing like how they did up there.
Yeah, and turn it into more and more cavities because you don't need to use a lot of material to fill in between those cavities. So yeah, you can be using that as a means of, you can throw insulation in there.
And then, have you seen any, like, just looking at it, it doesn't look like it would be well insulated. Do you think that has much insulation, or do you think that there is
by concrete itself, no, but you got to put in some serious insulating material into it to make it thermally performant.
But it looks pretty thick. Like I don't know how thick that is, but it looks pretty thick. I have a friend whose dad is in construction and lives in like a solid log house, like logs this big, all laid down to build a really nice big house. And his dad says that the log house is very well insulated just from all the mass. So if concrete was at all like that, then it could be well insulated.
Yeah, concrete is highly conductive, so it doesn't have that part, but
okay.
Yeah.
Cool.
Mm-hmm. All right, we'll leave it at that. Thank you for your attention. Cool. Let's build some open source 3D printers for construction. We're going to get to that soon.
That's a boy not. Open source.